19 and 20 are very similar. What we're going to do is expand on the idea of the equilibrium, but at this time we're going to be using a special type of chemicals, which are the acids and the bases, and they have special properties because they contain or will provide in a solution a hydrogen or a hydroxide ion. And those two ions will make a solution caustic or corrosive. So these have a special property, but they are still chemicals. These are still chemical reactions, so they will follow all the rules we've covered for equilibrium. Oh, excuse me. So these chapters do meld very well together, so you will be able to use the calculations and equations from chapter 19 and apply them to the new material in 20, which is good because repetitiveness is awesome for studying, because then there's only one equation and a couple ways to do a calculation you have to remember. All right, so for acid-base, there are 3 different definitions for acids and bases, and that is dependent on the way that you are looking at an acid and base. They all come down to the exact same properties. It's just the way in which you define those properties. So we'll start with the easiest one here, which is going to be the Arrhenius definition of acids. And what Arrhenius says about acids and bases is that if you put an acid into a solution, it is going to provide or create a hydrogen ion. If you put a base in a solution or in water, it is going to provide you a hydroxide ion. So how does that work? Basically, you take an acid, here's an acid, HCl, and you are going to put that into water. You'll get an H plus and a Cl minus when they dissociate. So this is an ionic compound. So when you place it in water, it dissociates into its ions, which in this case are hydrogen and a chlorine ion. So by Arrhenius definition, HCl or hydrochloric acid is an acid because it provides this hydrogen ion. So same thing, you put a base into water, it will dissociate into, like sodium hydroxide here, will become a sodium ion and a hydroxide ion. That is just dissociation of an ionic compound in water. We've done this since 112. Okay. But now we have a new definition which now makes these not only ionic compounds, but special ionic compounds called acids and bases. And dependent on what ion is formed in water will depend on what acid, or whether you have an acid or a base, right? By Arrhenius, you can also just look at the compound. HCl has a hydrogen, so it should be assumed when you see that when you put it in water, a hydrogen ion will form. This has an OH, which means that a hydroxide will form, right? So by Arrhenius, just by visual inspection, you should be able to tell what is an acid, what is a base. All right.
Doesn't look French.
Not at all. The slash through the O, I think, gives it away. Bronsted-Lowry is the next definition for acids and bases, and this is going to be more on a mechanism base. You're going to use this in order to understand what happens when acids and bases react with each other, or with water, or with any other kind of substance. You can use the Bronsted-Lowry definition. And what this is going to define an acid as is a proton or hydrogen donor. An H plus is called a proton. If you think back to what an atom is and how protons and neutrons and electrons work, you will understand where the word proton comes from for an ion that is H+. That means that it is a hydrogen atom that is missing an electron. And if you think back to what that is, you'll understand that it is indeed one proton. So an H+ is called a proton. If you don't understand, draw a hydrogen plus atom out. All right? A base is anything that will accept that hydrogen. So if you can look at the molecule that is being reacted and it will accept a hydrogen, it will be a base by this definition. If it has a hydrogen to donate, it will be an acid. So if you look at the HCl again here, for example, it has a hydrogen here that will very easily be donated, so that would be an acid also by Bronsted-Lowry definition. All right, so how does this work? Let's take HCl, which I just said was an acid, and we're going to react this in water. Okay, so this one is an acid. It has a hydrogen to donate. So by Bronsted-Lowry definition of this reaction, the hydrogen from the HCl is going to be donated to the water. The water will accept that proton, which means that in this specific reaction, water is acting as a base by the Bronsted-Lowry definition. So water can be an acid or a base or act like one, depending on if it is with a stronger acid or a stronger base, right? So what you get is this Cl ion that you got from before, and with the water having an extra hydrogen, you form H3O. That is called a hydronium ion. This is actually how acids react in water. The one I drew here was just by definition of Arrhenius. This is the way we would do a normal ionic compound. But with acids, the hydrogen here will not exist in water by itself. You do not put HCl into a solution into water, make a solution, and have hydrogen ions floating around. That is not the true situation, because HCl is also, by definition, a Bronsted-Lowry acid, so it will actually donate that hydrogen to water that it's being mixed in with. So the ion that you get out, the positive one, instead of an H+, you get the hydronium ion. So anytime you react a base or an acid in water, you want to write this reaction out instead of this one, because this one is more truthful. Okay, so use Bronsted-Lowry definition with acids pretty much all the time, except for when you're just visually inspecting molecules to see if they're acids. Then you can use Arrhenius. The last one is a Lewis acid and base, and really this is going to be more of an organic mechanism definition, but if you have organic chem coming up, it'll be a good idea for you to start thinking about using all compounds in a different way than what we've been doing so far. By a Lewis acid and base, right? Now when you talk about the Lewis acids and bases, we are talking about moving electrons around. In an organic, you will focus on electron pairs, not on the actual atoms that are reacting. So this is just a different way of looking at how these work. So two waters. All right, so there's our two molecules. We wanted to draw those out using the Lewis dot structures so that we can identify lone pairs, because that's what's going to happen. Electron pairs are lone pairs on your structure. So your base is an electron pair donor, so we're going to say this one is a base. So what's going to happen is that the electrons here are going to go over here, and they're going to donate to this hydrogen here. And what's going to happen when it does that is that it's actually going to take this, what it's doing is taking the lone pair here and offering to make a bond with that hydrogen. So that's what's happening, is it comes over here, offers itself to this hydrogen, the hydrogen then becomes removed from this oxygen, allowing it to now bond here. So what you get is a hydrogen that moves from here so the electron pair goes here, donates itself here, the hydrogen moves where the lone pair is. So here's a lone pair, and here's your hydrogen where the lone pair used to be. Right? So now it's moved, and so you end up with, again, this is a hydronium ion, and this is a hydroxide ion. Right? Yeah, those are the definitions. All right. So, all right, so there's your three different definitions, and you're going to be using those depending on the situation that you're in. Now, the last one there will most likely only be used in organic chemistry or anytime you're interested in what electrons are doing. But for us, mostly what we're going to use is going to be a combination of Arrhenius and the Bronsted-Lowry definitions. So here's something you may not know about water. Which, if you do any more chemistry, will probably be a good thing to at least have in the back of your mind when you are talking about anything that happens in a solution. Because water is not just in the form of H2O. That is what we've said it's in so far, right? But as you can see in the previous reaction that I did here, you see that water molecules actually can react with each other. So in pure water, not only do you have H2O, but you also have two other species that exist. The hydronium ion and the hydroxide ion, the two that I just drew there. So without the electron transfer, we can redraw this reaction as molecular formulas. Okay, so this reaction happens in water with itself at room temperature, no special conditions needed. This is in equilibrium. A two-sided, two-way reaction, so we have a forward motion and a backward motion, which will eventually go into equilibrium. So, of course, that's a reversible reaction, which leads to equilibrium, so they're not a direct connection there, but close enough. All right, so what's happening here is called autoionization. That's what water does because it does not need any other reacting species. It does not, like I said, need any super special conditions. It just needs to be water in its pure form, just sitting there. Okay, So it does exist with these two already in it. And these are the two that will make something basic or acidic, right? Because this ion here would make it acidic. This ion here comes from a base, which would make it basic. But since it is here in equal amounts, the two concentrations equal each other, so a solution of water is neutral. It is neither acidic, overly acidic, or overly basic. So this is going to be the whole idea behind acid-base, is balancing the concentration of these two ions here. By an equilibrium constant here, we could actually get the equation for the equilibrium of this reaction. But these two are liquids, right? So equilibrium does not describe a liquid at all. So those are not in our equation here. So the equilibrium constant for water only depends on the concentration of the two ions that are formed. Okay, this here, relating back to the last chapter, would be called the equilibrium constant of water dissociation, because that's what it is. But it has a different name since it is water. Another name for it is the ion product constant. So two technical names for it. If you're looking back at last chapter, it would be called the equilibrium constant of the dissociation of water, because that's the reaction that we're doing. It is also called the ion product constant because it is the product of two ions. So pretty straightforward there. So there are two different ways to determine that one here. All right, KW is 1 times 10, 1.0 times 10 to the minus 14 molarity squared. It's the product of two concentrations, that's why the molarity is squared. All right, so what happens when KW is very, very, very small? Which side is the equilibrium on of the reaction?
Left side.
The left side. Because it would generally be over the reactants, right? These are products over reactants is the general equilibrium, right? So if this is very low, that means that even though these concentrations aren't in here, the concentration of your reactant is very high. So the equilibrium is set to the left. Since KW is small, the equilibrium is to the left. And that is why you don't talk a whole lot about the ions in water, is because most of the water is in the water form. Okay, so most of water, if we could break it down, most of it would be water molecules. But you cannot, when you're talking about straight chemistry, cannot defy the fact that they are actually there, even if they are only in trace amounts, because they can become important depending on the other constants that you have. So you have to make sure you're always going back and relying back to this constant when you are working in a solution of water. Because if the equilibrium constant for your solution is close to or less than this, you will have to take into account the equilibrium of water. All right, so always keep that in mind. But in most cases, your equilibrium constant will be higher than the dissociation of water, this ion product constant. Okay, so remember this right here because it is going to become important for some of our calculations later. So do remember that the ion product constant of water is 1 times 10 to the minus 14 m squared. All right, if we look at our equation here, we have the concentration of the two ions here. And per the reaction, what are the ratios of these constants that are being formed? They're stoichiometric values, 1 to 1, right? So for every 1 and 1 of these that react, you get 1 of each of these, right? So in the water dissociation, the concentration of the hydronium ion is equal to the concentration of the hydroxide ion, right? And the equation that we have for Kw is the product of those two. Well, if they're equal, we can actually find the concentration of one of these, can't we? Or actually both of them. If they're equal to each other, right? It's just pretty much that divided by 2. But we'll figure it out mathematically. If this one's equal to this one, all we have to do is plug one of these in for the other. So let's plug in this one for H3O. So then we have that Kw is equal to OH times OH. Okay, so now you have OH squared I guess it's a square root. All right, if you want the concentration then of OH, you take the square root of this. (1.0 times 10 to the minus 7). Okay, so the concentration of the hydroxide ions in pure water is 1 times 10 to the minus 7th. And since the concentrations are equal, it's also 1 times 10 to the minus 7. This will help us in a solution where we add an acid or a base to it and make a solution, because the concentrations here are no longer going to be equal. So we can say something about these concentrations just by comparison, whether or not we have an acidic or basic solution when we make one. Because if the two of them are equal to each other, as we see there, the solution is going to be neutral. Okay, what happens if we increase the amount of H3O? Which way do you think this solution goes? Neutral, acidic, basic? Acidic, right? Because if our concentration of the H3O increases, that's the acid part of it. So we would say that this situation will give us an acidic solution. Now, how acidic, we don't know yet, but we just know that it will be more acidic. So if we have the other way around, and now the concentration of OH becomes greater, then we have, of course, the opposite situation, where now we are going to be working with a basic solution. All right. One of the main concepts of the acid and bases is the fact that for each acid and each base category, we have two different types. We talked about electrolytes a little bit, about how when an ionic compound breaks up, you get electrolytes, and there are strong ones and there are weak ones. Strong electrolytes come from an ionic compound that dissociates 100%. So if all of that compound, every single molecule you put in there breaks down into its ions, it is considered a strong electrolyte. An electrolyte is whether or not it carries a current. So a strong electrolyte has ions, which are charges, which will very easily move a current. A weak electrolyte, on the other hand, was an ionic compound that breaks down only a small percentage, which means you only have a small percentage of ions, which will carry a weak current. It will carry a current, but it'll be weak. So that's where the words strong and weak come from. Our last one in there was a non-electrolyte, which was a covalent compound that does not break into ions at all. So that would be a non-metal with a non-metal. All right, so that's what we talked about in 112. We're going to do the same thing with our acids and bases, is that we will have strong acids and bases and we will have weak acids and bases, all right? And they go pretty much by the same definition as the electrolytes, only we aren't worried about it carrying a current. We are just worried about how much for an acid of this H3O we're going to get, and for a base, how much OH we're going to get. This is what we're going to be focusing on. Concentration of these ions that are created from an acid or from a base when it is put into a solution. All right, so that's why we're going to define these and remember a few of these by what category they go into. So if you have a strong acid, it is going to dissociate 100%. That means that when you put it in water, every molecule of that acid will break down into the ions. So again, if we look at our HCl, it's an acid, so water is going to be part of this reaction. We are going to get Cl- and H3O out of this. Okay, so now you see where that concentration of H3O comes from, is the breakdown of this acid in the water. All right. This is considered a strong acid, which means that its dissociation is 100%. What that means is there's no going back. This is not an equilibrium reaction anymore, because there is no way for these to recombine and go back and form this HCl. Okay. So 100% one-way trip. This will not be related to the equilibrium, because we will only have this one and it will not go backwards. All right, how do you know if it's strong acid or a weak acid? Well, you either need to know what each one of them does when they form their other ion, what's called the anion in water. Does it salivate or not? If it completely salivates, that is the reason why it will not reform. Salivate means that it gets completely surrounded by water molecules when it's dissolved. And when this happens, there is no way for this ion to come into contact with this one again, right? You'll have to know what each one of the acids breaks down into the anion, and you will need to know whether or not that anion is solubilized in water or not. The other way that you can do this is you can remember a list of strong acids. There are only 6 of them, and there are 9 strong bases, and you will, by next week, need to have them memorized. So I would start right away. All right, so your list of strong acids. is perchloric acid, sulfuric acid, hydroiodonic acid, hydrobromic acid, hydrochloric acid, and nitric acid. Notice that the acids do not have their ionic compound name. When they become an acid, when they are dissolved in water, they are no longer called hydrogen chloride, hydrogen bromide, hydrogen nitrate. They are called nitric acid. So when it is a compound like this one here, the polyatomic ion, you name this one first, hence why it's called nitric acid, and it doesn't have the hydrogen in it at all. When it has a hydrogen and it's one of our halogens, you put the word hydro in front, so you get hydrochloric acid, hydrobromic acid, hydroiodonic acid. Okay. This is a sulfate, so this is called sulfuric acid. This is a perchlorate, so it's called perchloric acid. So you drop the end of the polyatomic ion name and you put ic acid. Ic acid. And then if it is a halogen, you call it hydro, the halogen's name, ic acid. So hydrobromic, hydrochloric, hydroiodonic.
Say the second one again.
Which one? Sulfuric, from the sulfate. You take the full sulfate and make sulfuric. Okay. Those come from just familiarity, just saying them over and over again, and they're named in your chapter too. But those are the ones that have different names. But you notice when I did the base, bases just have the ionic compound name, like sodium hydroxide is the same as when you named it back in the day. All right. So these are the ones you'll want to remember. So 3 of these are polyatomic ions, so you just have to memorize those ones. These ones are all from halogens. So if you look on your periodic table and you circle it, those 3, it'll help you remember the 3 acids. It will not be fluorine. Fluorine is way too electronegative to be a strong acid. So that one you will not have. It's the 3 below it that will, and you don't have what arsenic isn't one of those. So it's the 3 under fluorine, not including fluorine. So you have 3 of them down there, and then you just have to remember your 3 that are polyatomic
So are we
ions.
gonna be tested on how they break apart and their names, like knowing their exact name?
Not their names, no. No. That's just something that's good to know because you're going to hear those names.
After this class.
Well, if you live in the real world, you will eventually hear those names. So maybe. If you shut yourself in a closet, maybe not. But, well, you need them for the test next week, so it'd be a good idea to at least momentarily remember them.
They'll fit on my hand.
Fantastic.
And you know
What
who's
about
getting
us
his
with
hands
small
checked?
hands? That's unfair.
You better be good at drawing, you don't have sweaty hands then.
Yeah, he's gonna come in and be like, they'll be gone.
Everybody wash your hands before the test.
I'll make you all get up and wash your hands.
I only use this hand though.
There's
Smells
nothing
good,
here,
Mom.
there's nothing here.
Wear sandals that day.
All right, there's a list of strong bases too. There are 9 of these you will need to know.
9.
Good thing is, these are all related to the front of the periodic table. So a bunch of these come from your alkaline earth metals. That's the first 2 columns. And those come from the 7th. So bases are of course going to be the positive one or negative ones, so they're all, or acids will be negative, so they're all going to come from the negative side of the periodic table. The ones that make negative ions, that's what I mean. So that will be your halogens, the negative ones. So, and over here, to make your bases, you need the positive, the metals. So it's going to come from your alkaline and alkaline earth metal categories. So a bunch of these will be easy to remember because the first 5 of them come from the first column of the periodic table. Lithium, sodium, potassium, rubidium, cesium.
Does this mean I need 2 hands?
Probably. That's good you have 2 hands, so. Just don't do anything before the test that makes you wash your hand like this. All right, so from the periodic table, it's all but francium in that first row, all make bases, which will all be strong. There are 2 from the second row, calcium and strontium. So there you go. If you circle those ones on your periodic table, and remember those are from your periodic table, all you need to do is pull out your periodic table, circle those again, and you'll know at least most of the strong acids and bases. -3 there, and there are those are 2. Oh, one more. Barium. Can't forget that. Okay, so there's 3 from the second row. So there's all your ones for bases. There is one that is not in that one. And that is thallium. Thallium hydroxide. All right, so those are the ones you need to memorize. Again, most of the bases you can get just off the periodic table. Most of the first column minus francium, plus the second column, which starts at calcium, goes down to barium. Right? I think barium's the last one. Yep, calcium, strontium, barium. So you knock the first 2 in the second row. Knock those ones off, but the rest of them make hydroxides minus francium, and the one next to it, the bottom one's always cut off.
Why is it francium base? Is it too reactive?
Probably a base, but it's not strong. So these are only the strong ones. Any of the other ones that form bases will be weak bases or weak acids. So if it's not one of these, not one of those, it's weak, which will be really easy to remember once you have these ones down. It's not this, it's weak. Any other compound that is considered an acid or a base is weak. That's why you have to memorize the strong ones. All right. So, how are we going to measure this concentration? Because this, for acids and bases, the measurement of the concentration of the hydronium and the hydroxide ion are going to be our #1 concern. That is what we're always going to want to be looking for. Now, there is a scale that is used in order to measure the concentration, which is called the pH scale. When you use this in a lab, you just have a piece of litmus paper, you put your acid or base on it, it'll change the color, you measure it up to the scale, and the scale will read off your pH for you. Okay? And your pH on that scale is going to be related to the concentration of the hydronium ion. So when you're using the pH scale, you want to know how acidic that solution is. But you might say, with the pH scale, it goes from 1 to 14, 7 is neutral, 1 to 7 is an acid, and 7, or little above 7 to 14 is a base. So if it is measuring the acidity, why is the acidity not the high pH number? And that is because this concentration is what makes it acidic. It's not the pH. So we have to answer that question, we have to look what the relationship between the concentration of the hydronium and pH are. pH is on a logarithmic scale. So to get the pH from the concentration of the hydronium, you must take the negative log of that value. By doing that, as this increases, the pH will decrease. So that is why acids, the more acidic, the stronger the acid, the more H3O, the lower the pH. Yes?
Is it the negative log of the concentration of the hydronium?
Yes,
Okay.
so this. Make it more clear. There we go. So with this, this is definitely one of the equations you will want to know, because this is going to get you from the concentration of the H3O off of any concentration that is measured, and it will take you to the pH that you should get off the pH scale. So this will take you from the chemistry, the concentration, to something in the realistic world in experimentation that you can measure. So that's always a good thing. Now, if you have the pH and you want to know the concentration, you can take the anti-log of both sides, and this is log 10. So on your calculators, you're going to be using the log function, which by definition starts at log 10. Other than that, you have to punch it in your calculator to see what log value you're going to use, log 3 or whatnot. Here, we're just going to use log 10, which is good on your calculator. You don't have to do anything special. You just hit log, and the anti-log is the second log function, or whatever your second, normally it's the second or shift key. Whatever's above your log will be the anti-log, which is 10 to the anti-log is 10 to the x. So if you want to know the concentration of your hydronium ion, all you have to do is take the anti-log, which is 10 to the negative pH. Okay. And how would I get that? I would take 10 to each side here, 10 to the negative log would be negative, so you switch it over here and you get 10 to the negative pH. Solve for your concentration. It's just log-based math, so any college algebra book will have how to do this. Okay, the P function is not special to chemistry. It is just used by chemists to do pH scaling, because the concentration of H3O could be anywhere from 0 to 10 to the minus 14 molar. And that many exponents you do not want to deal with. So in order to remove the exponents, the P function is used, and that's where we got the pH from, which is a log-based system, which allows you to use a numerical base from 1 to 14. Makes it a lot easier to work with mathematically than concentration. Okay? If you're working with a base, we can use these same two equations, only we can modify them to measure the concentration of the OH instead of the H3O. And all we have to do is change the P function from pH to POH. If we want to know the concentration of the OH, we want to take the negative log of the concentration of the OH, or if we want to know that, we will take 10 to the negative POH. All right? So all I did to change those two equations, once you memorize this one, and if you don't know how to do anti-log, this one as well will be your next one. If you have these two memorized, the other two come naturally by just taking the hydrogen, the acid version of your equation, and changing it to a base version, the OH of your equation. Right? So you see how you can switch that over? You do not have to memorize 4 equations. You just have to memorize this one, maybe this one, and then the other two are just exchanging this value and this value with the ones for OH. Okay, how do we go from one to the other? Real quick, I'll do that, because you will most likely from pH only ever get the concentration of H3O. So if you want the concentration of OH or the POH, that is not something that can be measured. It must be calculated. So we need to know the relationship between pH and POH. And that's going to come back to our ion product. constant for water. Because this is the easiest way to relate those two together, correct? Because we know the product of those two is 1 times 10 to the minus 14. So if we take the negative log of both sides, because we want to know pH versus pOH, we are going to get the log of H3O negative log plus the negative log of OH. Alright, so we get something called the pKw. We get pH plus pOH. And pKw is just the negative log of this. So the pKw is 14. So 14 equals pH plus pOH. So if you have one of these values and you need the other one, you just take 14 minus that value. Which is nice because our highest pH is 14, so it all comes back to 14. 7 is neutral and 14 is your number, is the concentration. It's your ion product constant, 10 to the negative 14. It is also your pKw, 14, so it all comes back to 14 or 7. So those are good numbers for you to remember. Okay. So remember that these were considered neutral. They had a concentration of 1 times 10 to the minus 7. Right, to get that 1 times 10 to the minus 14. When they are neutral, so a pH, so if you take the negative log of 10 to the minus 17 or 7, if you take this, that equals 7. So a pH of 7 is neutral, right? So it all works back around. And 14 minus 7 will give you a pOH also of 7. So they're equal to each other, so both are neutral. So the math there all works out. All right. And if you want to know the pH of a concentration like that, it's always going to be whatever that negative exponent is, you just make it positive. So did you see that when we took the negative log of 1 to the minus 14, it ended up 14? And when we took the negative log of 1 to the minus 7, we got 7. So if your pH is 7, the concentration of your ion is 1 times 10 to the minus 7. So the only time you have to worry about these calculations using these is when your pH isn't a whole number. So if your pH is 8, the concentration of your ion, the H3O, is 1 times 10 to the minus 8. Okay, so that one's easy to mix back and forth. It's just when you get pHs, if you read it off of a digital pH meter, you'll get pHs like 7.14. Then you have to use these, all right? But as long as it's 1 times 10 to the negative something, the pH is always that value positive, okay? So that can shorthand some of the math for you. And you'll notice that if you type it in your calculator, you're going to get that number. So either way, you can work it or not. Okay, movies. All right, so let's keep it on here. Okay, so we talked about the strong acids and bases, and they are going to dissociate completely into ions. And that's going to give a special view for us when we are working with, do you have a question?
Yeah, so like the bases, they dissociate too, or no?
Yes, strong
Oh.
bases will dissociate 100% as well. So anything that I described as a strong acid will correlate to the strong bases as well.
So like that lithium one, it would be Li and then OH on one side. type of stuff?
Yep, and 100%, so you would get all lithium ions, all lithium hydroxide, and no lithium hydroxide molecules.
Okay.
Okay. Okay, so we did talk about the HCl here. When it dissociates 100% in water. So we will get our Cl minus and our H3O there, and that was just done by Bronson-Glory. The hydrogen went there, donated to the water, creates the hydronium ion. All right, and what we are interested in again is how much of this. Okay, well, the good thing about the strong acids is that they're going to completely dissociate, which now means that if we have an HCl and we have the initial concentration of the HCl at 0.1 molar, so of course this of course is the solid version of it, but when we put it in the solution we are creating is a 0.1 molar solution. So I won't put it under there because that implies that that has that molarity. So it is a 0.1 molarity solution of HCl. What it means if it is a strong acid, it means that the concentration of the H3O is equal to the concentration of the solution. So when we create this solution, right, it will also be equal to the concentration of the Cl, but again, that's not what makes it acidic. So this part of it is not something we concentrate on. But it does work that way. These are 1-to-1. It completely dissociates, so everything in that solution is these two ions. So of course, we would create exactly that concentration of H3O. So if you have a strong acid, the concentration of solution is equal to the concentration of your H3O. All right? But what if we have a weak acid? If we have a weak acid, we do not have a complete dissociation. So let's look at hydrofluoric acid. That is our hydrogen fluoride. When we put it in water, we get the fluorine ion. Assume that starts solar power. All right. So we made this solution here of HF in water. It reacted here. This is a weak acid, meaning that it does not have 100% dissociation. Okay, so only some of it dissociates. So this is an equilibrium equation because when this reacts with water, breaks down in the ions can reform because the fluorine does not get completely solvated in water, so it is open to recombine with the H3O, reforming water in the HF. So these are working at the same time, one going forward, one in the reverse, so we do have an equilibrium working here. All right, so if we have a weak acid, we are going to have less of the H3O overall. If we start with the same concentration of both of these, we are going to have less H3O in our weak acid because it does not break completely down. So Let's say that we took the pH of these two solutions. Okay, so we have two solutions, same concentration. One's a strong acid, one is a weak acid. We find the pH of the two is 1 versus 2.1, which makes sense because the less concentration of H3O, the higher the pH is going to get. Lower concentration of H3O is a higher pH. They're inverse of each other. The concentration of the H3O here is identical to the concentration of the solution created. The concentration of the H3O is going to be 7.9 times 10 to the minus 3 molar. So you notice that it is lower than 0.1, which is what you would expect because of the incomplete dissociation. Now, by knowing these values, we can actually determine how much of this solution dissociated, how much of that ionic compound dissociated. In the HCl, to find the amount of dissociation or percent dissociation, we want to compare the concentration of the H3O that was produced to the original concentration of the solution of HCl. If we do that, multiply by 100, we will get the percent dissociation. In this case, %, right? That's what you wanted there. Okay. We can use the same process to figure out how much of our HF dissociated by taking the concentration of the H3O from that and compare it to the concentration that we created of the H, multiply by 100 again. So now so only about 7 to 8, well, approximately 8% dissociated. So this one is 100%. This one is approximately 8 or 7.9%. So we can determine the amount of dissociation if we know the concentration of that ion. If we find the pH, we can get that, right? Because all we have to do is take 10 to the negative 2.10. So we could do this in the lab. Take the pH, take 10 to the minus, and it should be this. And then we take the two, divide them out, and we will get our answer there. Okay. All right, so we're going to view these a little different if they are a weak acid or if they are a strong acid. We're going to have an equilibrium constant that will also describe the dissociation of these reactions here in the same way that we described the equilibrium constant. But since these are all dissociation reactions, we will call these dissociation constants. So if we put a generic acid in water, creating a solution, an acidic solution, HA is going to be our generic term for any acid. We put that one in water. That is aqueous. will get A minus plus our hydronium ion. All right. So, acid plus water gives us that anion from the acid, and then the H3O. That's how they're all going to break up. If you plug in the HCl, you can see that A in this case is the chlorine ion. So A minus would be chlorine minus. Okay? So just generic terms, and we're going to define the equilibrium constant as Ka. Now, instead of having the other subscripts, we put the A in there, which is going to say this is the dissociation constant of an acid. Okay, so instead of equilibrium, we will call this and the little a there stands for the dissociation constant of an acid. What do you think the dissociation constant for a base would look like? Yeah, good job. So Ka for an acid, Kb for the dissociation of a base. So again, these are very linear with each other. So we talk about one, but it also gives you ideas about the other one as well. We can use the same thing. Okay, so for the equilibrium equation, we just put products over reactants. Water is not included because it is a liquid. All right, so those, they all have a subscript of 1 because each of these have a coefficient of 1. So that will describe how much this acid dissociates. So each one of these Kas gives us a little insight into that acid. Now, the larger Ka is, the more acidic the solution is, or the stronger the acid is. Because if Ka increases, that means that this is large, the concentration of H3O. And as that increases, the acid becomes stronger. So Ka will tell you about the strength of the acid. Not that you don't have to memorize them, you are better off memorizing them than trying to relate, make sure, hoping that I give you every Ka for every acid. That won't happen, so you need to memorize the list. But you can compare the Kas of two acids and tell which one dissociates further and which one has a higher concentration of H3O, which means which one's a stronger acid. Okay. So, of course, the smaller it is, the lower the number. The less acidic the solution is, the less dissociation, so the more of the compound, the ionic compound you will have. All right. So, one of the best weak acids to study is actually an organic one. But it's also vinegar, so you've seen this before, you just may not have known the chemical formula for it. This is a carboxylic acid called acetic acid. Carboxylic acids are organic compounds, that's why. What does it look like? That's a Lewis structure for it, right? Well, the organic structure doesn't have all the dots. Lewis dot would have the dots, but unnecessary in organic chem. You know they're there. All right, this is acetic acid. It's one of the better weak acids to study. That's why the book goes through an entire section on explaining what it is to you. Really, what you need to know is that if it has this acid out here at the end, that hydrogen, that's the acid part. it won't give away these hydrogens on the carbon, because carbon-hydrogen bonds are too strong. They're covalent as well. Do you see this one here? This one actually is a hydroxide group. You can pull that hydrogen off fairly easily. Okay. So there's like a little chemistry behind it, but just believe me, this hydrogen out here can be pulled off. And if it says it's an acid, like acetic acid, that means there's a hydrogen available. Most acids are labeled in the name, which is kind of nice. All right, so you put this guy with water as well. We will get a crazy ion where we're going to just pull that hydrogen off, put a negative sign next to that oxygen there. And our H3O. All right, so basically all I did, Bronsted-Lowry definition, this is an acid, that hydrogen was the one that was open to pull off, and all I did was donate it to that thing. So it's just like using the HCl, it's just instead of the chlorine ion being that A minus, you get this guy right here minus the hydrogen as your ion. Of course, being organic, it has a large organic name, acetic acetate ion. So you take the acetic and it's now acetate. Take the ick off, ick acid, and put 8 at the end. Makes the ion. Okay, so a little bit about that. All right, so if we want to know the Ka for this, this is a weak acid because it was not listed as one of our strong ones, so that's why I know that. It's not strong, so it has to be weak. So it has a Ka, it has a less than 100% dissociation. Right, so we need to figure out the Ka. We can write out the equilibrium equation for this. Comparing the concentration of the ion to the concentration of the acid to the concentration of the carboxylic acid, the vinegar. All right, this Ka is experimentally determined to be 1.8 times 10 to the minus 5 at room temperature. Okay, so a couple of things to think about with this Ka value here. One, it's small, 10 to the minus 5th, that's a pretty small number. But it's not as small as the Kw for water. So when we do calculations for this guy here, it's large enough that we do not have to take into consideration the H3O from the water. That's what we always want to be looking for. Do we have to include H3O from water? Most of the time we try to develop experiments where you do not need that information. It makes it a little bit more complex. All right. So how are we going to do calculations on these acids, especially the weak ones, using the information from last chapter and this chapter? So the question will go something like this. We have a 0.05 molar acetic acid solution. Okay, so that's the acetic acid there that we just described. We have a solution of that. And we want to know, what can we expect the pH of that to be? Okay. Well, the pH is related to the concentration of the H3O. So to determine the pH of this solution, we need to know the concentration of the H3O. It is not 1:1 because it's not a strong acid. We can't assume it's 0.05 molar. We're going to assume that it's less than that value. Okay. So what we want to do here is we want to determine the concentration that concentration at equilibrium. So, since it is an equilibrium question as well, these are the concentrations we want. When this reaction, this dissociation reaches equilibrium, what is the concentration of our H3O? We will have no information on water because it is a liquid. That concentration does not vary enough to be included, so we leave it out. So we want to know the initial change and equilibrium of the vinegar, which the solution concentration starts off at 0.5 molar. These two do not exist at the beginning, so they start off at 0. If their concentrations are not given in the question, they are 0 at the beginning, the initial. Okay, so the initial concentration is all on the acetic acid. This is going to change by X. All of the coefficients are 1 here, so X is going to be our change for all of these. Now, if this had been 2, it would be a change of 2X. Remember that. The coefficient in the front is going to determine how many times X changes by. All right, so it's going to change by X since there was no value given. We assume an X. So the equilibrium concentration for this will be 0.05 molar minus X. This will be plus X, and this will also be plus X because it's 0 plus X is X. Okay. So we know our equilibrium equation. We wrote it over there. We actually know what our Ka is. So we can determine our unknown, our X value, which is the concentration of our H3O. Okay. We can do this in 2 methods. Okay. I'm going to show you both of them. So for the first one, we're going to put in these values here for our equation. So 1.8, 1.5, 8 equals concentration of our 2 ions here. That's X and X, so X squared over 0.05 molar minus X. All right, so that's the equation we need to solve for. The first method is using the quadratic equation. Basically what we do is we rearrange this guy until we get it in the form of X squared plus something X equals 0, and we use the quadratic equation, plus or minus b minus square root of p squared minus 4ac over 2a. That one, all right? You solve for it, you can use your solver. All right, that's the first method. You want to go through that when you're doing the equilibrium chapter here. All right, I'm going to teach you a new method that you can use in one condition. And here it is. Method 2's condition is we have a weak acid with a low value of Ka. Or, in respect, if it was a base, a weak base with a low Kb. So you can always take any acid and replace it with the base information here. All right. In this, what we are going to do is assume we have 0.5 molar in our denominator minus X. And that is the one that complicates this solution. So we're going to do an assumption here. And we're going to say that X is is much smaller than our concentration. So X isn't going to change that concentration by that much. Okay? And by doing that, we can say that this approximately equals 0.05 molar. If X is very, very small, it's not going to change it that much. So at the beginning, we're going to make this assumption. That's going to simplify our calculation quite a bit, because now we just have a number on the bottom. So we solve for this. We take this over here, we multiply the two together, we take the square root, we end up with X in our first iteration. Being 9.5 times 10 to the minus 4. All right, we made an approximation, so we cannot just take that as our answer. We can't take that as a given. What we have to do now is assume X is this, and then we need to go back and plug it in here and rework the calculation again. We're going to do that until two calculations in a row give us the exact same number. When we know that, we actually know that we're very, very close, if not on the exact answer. Okay? This is called the method of successive approximation. It's used when you can make very educated approximations like weak acids, low value of Ka. Okay, it has to meet certain requirements, but then you can use it because you can see that our approximation is very close because this is 10 to the minus 4, this is only 10 to the minus 2, so this is much, much smaller. Okay, so the approximation was good there. Okay, so what we're going to do is plug it back into our equation. Okay, so X squared equals that, the product of those two numbers. To get X, we take the square root of that product. Okay. So multiply these two together, take the square root, so X is going to equal, in this iteration, 0.94 times 10 to the minus 4 molarity. All right, successive approximations, so now it's a little lower than it was before, so we'll go back in here, replace that value, work it all back out. The next time you do it, you will get the same value. I just ran out of room. But plug it back in, stick it in here, it still ends up being this 0.049, so the rest of it works out exactly the same. The other way that I can do it is now if I want to check this work, if I don't believe it, plug this value in now for X here, and down here, and see if that statement is true. Plug this in, plug that in, see if it equals that. It does. Okay, so you can always go back and check it. If this statement is not true, then you know you did something wrong. Okay, so you can check it do your math over and over again. And then, of course, when you do these, to be more correct, they're not equal. It's approximate all the way down here. Okay, until you solve it and confirm that it's true. All right, so just a little different technicality there. All right, so by this second method, and then if you had plugged it in here, this is just more tedious of a method, so if there's a way to get around it, it's always a good idea to try, because that math is a lot less strenuous than trying to work out, unless you have the solver, that makes it a little bit less intensive. But you will find if you plug this one in, you will get the same answer for x. So, also shows that this works. All right, so we have the concentration now here of x being this. So your new concentration here is this, all right? So, because we assume this will be very, very small because it doesn't do 100% dissociation, it's weak, so you think that it's going to be less, and it does end up being that. Now, if you want the pH, you want to take negative log of the concentration of your hydronium ion, so negative log is 3.03. All right, so much higher, much lower concentration here than the 0.5 there, much higher pH, less acidic. All right, if you want to know the percent dissociation, you can get that as well. You could take the about 1.9%. So not a very large dissociation. Okay, so there's some math you can do, not new math, so this is good. It replaces, it goes right along with chapter 19, so again, same technique for each one, which will make at least this part of the calculations a lot smoother, because you already need to know this information, and now you have a little added bonus of an approximation that you can do as well to simplify some math. So next week on the test, if there's a couple of them where you need to use the quadratic equation, instead of figuring that whole beast out, you can just try to use that, especially for using weak acid calculations. Okay, so keep those approximations in mind. Okay. KAs can have a large range as well. You can see that one of our KAs here was 10 to the minus 5. So there we're using an exponent there, and you don't like to use these large ranges when working with acid base. So we also have a value that we can use called pKa, where you can take the Ka, take the negative log, and you will then be in the P function, which again gives you single digit values. Okay. So we will also, in next chapter, this is where pKa is going to become important. But if you want to put that on a scale, the pKa and therefore also pKb can be described. P is always big. I don't know why I keep making it so small. No, P is small. Sorry, I'll stop fighting with myself. All right, So we have those values as well. Again, just like pH. So this isn't a new equation. It's just describing a new value here, pKa and pKb, which just puts it on a smaller range. You'll appreciate it later with calculations with their single digits instead of being a lot of scientific notations. A lot of 10 to the minus 5s and 10s and 14s. Okay, back to a little bit more of our acid-base talk, a little bit about what the opposite of an acid and the opposite of a base is. They're called conjugates. So what we are going to have here are what are called conjugate acid-base pairs. They are always opposite of each other. So an acid which has gone through a calculation and has a product, or through a reaction and has a product, will have what is called a conjugate base. So acids make conjugate bases, bases make conjugate acids, and I'll explain why they're opposing each other. If we have an acid here, HA, we react it with water, which is going to act as a base in this case. We are going to get the acid, what's left of the acid, which is A, and what is created from the water, which is the hydronium ion. So that's our generic equation there for dissociation of an acid here in water, but we're going to use our Bronsted-Lowry definitions where an acid is a hydrogen donor, because in that case the hydrogen went to the water and created the hydronium ion. What was left up of the acid when the hydrogen went away was that anion, that A. Okay? What's left of the water after it goes through the Bronsted-Lowry definition, it takes that hydrogen and absorbs it and creates the hydronium ion. These are the pairs. This is an acid, so therefore the leftover at the end of the reaction that's left of the acid is called a conjugate base. Okay, so that would be this with this conjugate, or acid conjugate base pair. And there's your pairs. Okay, the base here, the water, the conjugate of that is the H3O, the hydronium, which we're going to call the conjugate acid. Why is that? It is because this can no longer be called a base. This cannot accept any more hydrogen. You can't put any more on here. So the only thing you can do is remove a hydrogen, so donating a hydrogen. So now the opposite of the base here becomes an acid, because now it is now the hydrogen donor. When this reaction goes back the other way to recreate the acid and the base, this is now the hydrogen donor, which is an acid, and this will now be the hydrogen acceptor. So by definition, this has to be a base. Okay? So a conjugate, or an acid becomes a conjugate base, and a base becomes a conjugate acid in their pairing. Okay? So that's how we're going to pair these two together. Okay. If you have a strong acid, you start with a strong acid. You are going to create the same thing with a base. If you start with a strong base, you will make a weak conjugate acid. If you start with a weak acid, like the acetic acid, the acetate ion that is created is a strong base. not a strong base. There you go, conjugate base. You don't have to memorize those ones.
So we don't have to memorize that.
Just remember that. You don't have to memorize strong conjugate acids. There's no list of those, just memorize strong acids, because yeah, this does not actually form a strong base. It's a strong conjugate base. It's a little different. All right, so when acids and bases react, you get a salt from that. The salt here can be neutral, acidic, or basic, depending on the strength of the acid in the base that was used. So the different salts that are created, the different ionic compounds, so salt is another word for an ionic compound. These salts can actually, they're not all neutral. They're assumed to be neutral, but they are not. So we have to have some basis behind how to determine if the salt of an acid-base reaction is going to be neutral, acidic, or basic. And this is why you memorize your strong acids and bases. You need to know if the acid or base that reacted to create that salt is strong or weak. A strong acid and a base, or a strong base, will create neutral salts. So if you react a strong acid like HCl with a strong base like NaOH, the salt you create is NaCl. Okay? So I have NaCl here, and when I break this down, I'll say, well, the base created from this salt, NaCl, when you look at it, you're going to get this as just a salt that's going to say, is this neutral, acidic, or basic? And you're going to have to figure this out. Okay, the salt here comes from a base, which is NaOH. You're going to have to just work that backwards. The Na becomes a positive ion, so the only thing you can create from Na plus is putting a hydroxide on it. Okay, you can't put an H on the front here and make an acid because they're both positives. So you got to think about that one. Got to think a little ionic chemistry here. The Cl here is minus, so the only thing you can form from that is the acid. So what you want to do when you see these salts is break them back into their acids and their bases. And then what you're going to do is remember NaOH is a strong base, and HCl is one of my strong acids. When they come together, these two form, the salt there is neutral if both of them are strong. So that's not or. A strong acid with a strong base gives a neutral salt. So what happens if one of the ones are weak? So weak acids have strong conjugate bases.
acid, let's think of weak acid. Oh, here we go. HF. That breaks down in water. Gives you,
Okay,
here, that's your strong conjugate base right there. All right, so this will react with water, creating your thing back, and all right, so here's how it goes. Weak acid dissociates in water, giving a strong conjugate base. The strong conjugate base reacts with water to give you back your weak acid and also a hydroxide ion. The hydroxide ion will make that solution basic. A strong acid will not do that. If you put this one in water, you would create the chlorine plus the hydronium. The chlorine ion will not react with water, so you will not get a hydroxide ion. Because this, remember, is solvated, which means it will not react with water, it will not react with this, it will not go backwards. So since it will not go backwards, it will not react with anything. Okay? So you can't get that basic solution from that. The weak base does the same thing. We'll make a strong conjugate acid. I wanted an example. Weak base. All the ones I'm thinking of are, oh, that's good. Francium hydroxide. I've never actually made this. It probably doesn't exist, but it's the only one I can think of. Oh. You don't need the water in the base. Right, so that breaks down in water. That makes a conjugate base here. So francium will react with water. There you go. There's an example. I don't know if it exists, but it works, so we'll use it. So if this one breaks out and makes that ion there, and that's what we're worried about right there. That's what's going to make our salt, right? It's not this one, it's this one here. So if it will react with water when it's created, and it will reform and make that acid there, you will get an acidic solution from a weak base. So all you have to do is just remember that weak, strong acids make the neutral salts. But if you have an acid, now let's say instead of NaCl, our acid that we get is NaF. This is going to be neutral because it is from a strong base. But when you work this one back to the acid, you get HF, which is weak, and strong acids are going to create the strong conjugate base, this F here, which is this one here. So when you have this in solution, the HF will react with water, and it's going to then create the HF and the OH. So this solution, this salt here, will be basic. See where I got that from? Okay, I'll have to look it up. But it's only if it's weak. If you work it back, that's why you have to memorize your acids and bases. If you work it back and it becomes a weak acid or a weak base, it will be the opposite of what it creates. This is an acid, so that will be basic. You just have to remember their opposite. Okay, so the other way around, if you have a weak base, so we have francium, so let's say instead we have francium chloride as a salt. Okay, the chloride goes back to being HCl, that is a strong acid, so this is neutral, so you will get nothing from this side. So it's all going to be dependent on this one. Well, francium hydroxide is not one of our bases, so since it goes back to being a base, this will be an acidic solution. Yes?
Why can't this Cl go back to NaCl? Why does it go to HCl?
Here,
Yeah.
there's no sodium.
There's
It only goes back to being either an acid or a base. So you can only add H or OH to it. No sodium in there.
also there's okay.
These are three different, this is example one of a salt. This is a different salt, and this is a third salt. Three different questions. If I have these salts in solution, if I make a solution out of this, will it be, if I put a pH meter in it, will it be acidic, basic, or neutral? And you decide. If they are both strong acids, if it is a strong acid, strong base, when you make it back, it will be neutral. If it is strong and weak, what if they're both weak when you work them backwards? Then you have to know their Ka and Kb. And the one that is stronger is the one that will stand out harder. That's where you're going to need Ka and Kb to compare them. So there's one more example I didn't go over there. If they're both weak when you bring them back, then you have to use Ka and Kb to compare them. Along with the larger of the two numbers is going to be the one that is what? Less or more? I'll leave you to figure that one out. That one's a good one. Okay, so just you have to remember in these ones. If you work it, you're always going to work it back from the salt to either the base, or the last one here will always go back to the acid, and then using your list of strong acids, strong bases, you will figure it out. If the acid is weak, it's basic. If the base is weak, it's acidic. It's always opposite of what it goes back to. Because we are talking about what happens when this ion reacts in water, it will become basic even though it comes from a weak acid. We are looking here at the francium. Francium is going to work, the francium in this salt is going to react with water to recreate that base, and it will also give you an acid, H3O, or H plus in that case, because I didn't write it out to make the H3O. All right. So, yeah, I'll just go over these last two things. Be done with this chapter. Last little concepts, and this is just going to be, again, leading on some acids have multiple hydrogens. they're called polyprotic acids. Remember, the H in front is a proton, so H plus and proton are interchangeable words. Okay, so polyprotic means that there are multiple H's, or H pluses. So something like this, H2SO4, sulfuric acid, one of our strong acids, it is a diprotic, polyprotic, di if there's two, tri if there's three, this one, and that'd be a tri. But they're all polyprotics. Okay. So if you have a polyprotic, that means that it has two protons to donate, which means that it can react with water twice. In the first reaction with water, it will completely dissociate into HSO4 minus plus H3O plus, because only one of these gets donated. One goes over here, but one stays. Only one hydrogen, because you're only making H3O, right? So you get this here, which is both a base and an acid, but we're going to continue using it as an acid because it can react a second time with water, this time as a weak acid because that's no longer a strong acid, and we will now get the sulfate ion plus H3O. Okay? So just keep that in mind when you're talking about acids, that there is a possibility of having multiple hydrogens on these ones, and you can see that first it will react as a strong acid, then it will react as, in the second part, as a weak acid. And the last concept here is the term amphoteric. It means that some compounds can act as both an acid and as a base. Examples of that: water. Because water is a hydrogen and a hydroxide combined. So it has a hydrogen to donate, but it can also, just like in this equation here by Bronsted-Lowry definition, can also accept a hydrogen. So water can act as both an acid and a base. It depends on what it is with. So far in all our examples here, it has been with a strong acid, but it will also act as an acid in the face of a strong base. All right? So it's amphoteric. Other ones that are amphoteric, let me think of it real quick. CO3. The bicarbonate ion is amphoteric because it can gain a hydrogen and become carbonic acid. It can lose a hydrogen and become a carbonate ion. Those are both stable ions, or one is an acid. So it's actually a diprotic. So you would see that sulfuric acid, the conjugate base of it there, is also amphoteric. It can gain a hydrogen, go back to being the sulfuric acid. It can lose a hydrogen and become the sulfate ion. So a lot of diprotics will be amphoteric as well. Right? These equations. So, the concentration of, what's the acid in the first one?
0.150.
Oh, no, what's the acid?
Oh, it's H3O.
OH negative?
No.
That's the
The
base.
acid,
CO4.
starts with an H.
Yeah, H3O plus.
Oh, HCO04.
HClO4.
Oh.
We're just naming out their
Just name
C.
everything.
It's best
The
you don't
C.
put any of those on the test.
Strong acid, that means that it completely dissociates, which means those three concentrations are equal to each other. So the concentration of this is 0.15, so the concentration of H3O is 0.15, and the concentration of the perchlorate ion is 0.15, or is it 0.1?
You're right, it's 0.150.
Okay, 0.150, yes. Can't forget that significant figure there. There we go. All right, so how, now the last one you want is that, right?
Back up, how are you getting H3O?
Because when
Because
it
you
breaks
put water
down.
there.
Pink water, okay.
So they give that to us?
Gotcha.
We did that like 16 times in class. You should know how to dissociate an acid and water.
No, it's not like that.
Oh,
No, it's like in the problem though, how they have it in the second part, and then in the first part they have the H3O, they'll give those to
It
us.
says in an aqueous solution.
that means this. In
That's
an
fine.
aqueous solution of salt, any ionic compound breaks down into its ions.
So it's basically connected. Okay,
The aqueous tells you that information. And since it's an acid, it's 100%, which means that all the concentration is here. That's why these two, it completely breaks down so the concentration of these two are equal to the concentration of the solution. Right? So the only thing you need left, right, is the OH, okay? The hydroxide ion. Okay, so this is where these come into play. We have the concentration of H3O so we can determine the pH. So that's the first step. We want to get the pH because the only gap that I gave you between pH and pOH is this equation here. So you need to get the pH, then you need to get the pOH, then you can get the concentration of the OH, right? So you have this information, so you can get this information. You have this, so then you can get this. Then you have this, so you can plug it in here and get this. Okay? So, let me show you how to do that.
So that POH,
So the
when
only
you think about
information.
that, is that like an inverse pH?
This,
No, POH.
no, pOH is the P function of the OH concentration.
What is?
That
what does
describes
have
the
to do with
base.
the P function.
P function is just a mathematical way of using log to get from large exponents down to single digits,
Okay.
ranges.
Okay.
Like the range that your value can be for pH is only 1 to 14.
Right.
But for concentration, it can be anywhere from plus 25, 10 to the 25th, to
Yeah.
10 to the minus 25th, and even farther than that. So we,
Okay.
that's such a huge range, it's hard to work with numbers like that, especially if you're graphing something.
Right.
How do you graph ranges of concentration that go from +5 to -5? You have this range that's like massive on your scale.
Right,
If you use pH, pH is only 1 to 14, so that's your range always when you graph.
Okay. Got it.
So, the only thing you have is the H3O, so you know the contribution of the acid. Well, we need to know the contribution, the base. This is your base ion, so we want to know that, how much base ion is in there. So, the only way we can do that is first determining pH. And we have the concentration of the H3O, so we're going to put that in here. Take the negative log. I don't have a calculator, so you're gonna have to do it.
Got it.
I got
1.41.
negative log, right?
0.8239.
Yeah, that's just when you do second log, right?
Negative log.
Negative log, so put in,
Just negative.
The negative?
And then log.
it's like next to your, there you go.
Gotcha.
8 to what?
39.
Let's go that
And a
way.
bunch of other numbers.
All right, so there's your pH. Now pH plus pOH is equal to 14. So to get pOH, you take 14 minus your pH, which is 14 minus 0.8239, which is 13 something.
13.176.
So there's your pOH. So now to get the concentration of OH, you take the anti-log. So you do negative POH, 10 to the negative POH. So
6.66.
take 10 to the negative 13.176 will give you what?
6.6666666. Just want you to know I find irony in that entire problem.
To the negative what?
14.
There you go. Should be really small, right? Because this is an acid. The OH will be very, very small. It's basically what's contributed by the water.